Hey, this is Horner, and this is part 6 of everything you need to know about rotational motion to pass the AP Physics 1 test. And we're going to talk a little bit about angular momentum. So we remember regular momentum is equal to mass times velocity. And if you remember the things that we've been doing, for example, if I want velocity and I know the angular velocity, I just multiply that times the radius. Same thing with acceleration. If I know the angular acceleration, I multiply that times the radius. If I want to find the displacement, I just take the angle and multiply it times the radius. So with this, I'm going to do the same thing. I'm just going to multiply times the radius. And that, when I do that, gives me angular momentum. So this R that I plug in and put right here is the same as my this is my angular momentum. So you'll see the equation down on the bottom. The only thing that we need to add is sometimes there's an angle associated with it. So you'll see this angle goes from the radius past the object, and then the angle comes back to the direction of the velocity. So that's where the angle comes from, and we're looking for the angular momentum using this equation. If I substitute in for my velocity, so if I substitute in omega r, so we're going to say L is equal to m, and then we're going to do omega r times r, I end up with the equation that you see here, mass times r squared times the angular speed. So this is another equation for angular momentum. There's one more, and if you remember, mr squared is actually the moment of inertia for a point particle. So that's mr squared. So now we can plug I in. So all three of these equations do the same thing. They just have different terms that they use for that. So that is angular momentum in a nutshell. You can think about some practical applications. For example, if I have a person who is on ice skates and they're spinning and they have arms out, they don't go very fast. But if they pull their arms in, they conserve that angular momentum, and because the radius gets smaller, their speed, tangential speed, has to get a lot higher, so they spin it a lot faster. Let's go ahead and take a look at the next equation. We know that the change of momentum is called impulse, so we called that J, and that's force times the change in time. Well, we can do the same type of thing for angular momentum, the change in angular momentum, but instead of force, remember we use torque, and we're going to leave the change in time the same. So this change in angular momentum is similar to impulse, which was the change in linear momentum. The very first problem that they want us to do goes back to the first equation that we did, and it says find the angular momentum for a 5 kilogram point particle located at 2.2, and we're looking at it standing here at the origin. So I'm going to draw my line, which will be my radius, and I'm going to extend it out. So this is my radius, and then I have an angle that that line that I extend out makes with the direction of the velocity. The velocity here is 2 meters per second linearly in a line from going to the right, and I know that the mass of this particle is 5 kilograms. So let's go ahead and use our first equation in order to solve this one. So we're going to say that L, which is our angular momentum, is equal to the mass times velocity times the radius times the sine of that angle. So here we've got our mass. Our mass is, let's see, it's 5. Our velocity is 2. And our radius. If I know that this is 2 and I know this is 2, then I know that the length of this side is going to be the square root. It's going to be this 2 times the square root of 2, because that's a 45, 45, 45, I'm sorry, 45, 45, 90 triangle. And so that's what this is. Then we're going to do the sine of 45 degrees, because this angle and this angle should be the same. And since this one's 45, this one's also got to be 45. If you do your math, you'll end up with 20, and then our unit here is a kilogram meter squared per second. And that is the unit we use for angular momentum. If we look at it and we're standing here at point P, so I'm going to get rid of everything. If I'm standing at point P, now what I get is L is equal to mvr, sine of the angle. So this is equal to the mass times the velocity times the radius. Now notice the radius is just 2, and then I'm going to do sine of the angle that I make with the direction of motion. So you notice that this angle now is 90 degrees, so that'd be the sine of 90. If I go through and do all that math, I end up again with 20 kilograms times a meter squared per second. If I look at the angular momentum standing at Q, so now I'm looking at the particle and it's going away from me. So because it's going away from me, there is no angle. And because there's no angle, when I do MVR, sine of the angle, since this angle is 0, then this whole thing becomes 0, and my final answer here is 0. It doesn't have any angular momentum if I'm standing at a point where it's going away from me. So 3 ways to think about angular momentum. It's the same particle moving with the same linear speed, but depending on where we stand, that changes the angle. So that's a little bit more difficult concept. You might have to go back and repeat that a couple of times. The next question here says Angela spins on a rotating pedestal with an angular velocity of 8 radians per second. Bob throws her an exercise ball which increases her moment of inertia from 2 to 2.5 kilograms times a meter squared. They want to know what is her angular velocity after catching the exercise ball. So if she catches something heavy, we can kind of reason that she probably will slow down because of the conservation of angular momentum. So let's check and see if that's right. Our original momentum here is equal to I omega, and that would be I omega, and then our final momentum here would be equal to just I omega. So let's find out what her speed is. These two things should be the same. Our original angular momentum should be equal to our final. So we're going to say I omega should be equal to I final omega final. And if we solve for omega, we get I original, omega original all over I. And this is the final moment of inertia. We know we started with 2 kilogram meter squared of inertia, and our original speed was 8. Down on the bottom, we have now 2.5 kilogram meter squared of rotational inertia. So if I multiply all those things together, I get 6.4, and then this is radians per second, and that is my final speed. For the next problem, I've got, I'm going to pull this one up a little bit. I have a disk with a moment of inertia, oops, too far, of 1 kilogram meter per second, kilogram times a meter squared. It spins about an axle through the center here, and has an angular velocity of 10. An identical disk, which is not rotating, is slid along the axle until it makes contact. When it does that, the whole thing slows down. The question is, what is their combined angular velocity? So we want to know how fast they're moving. So I know my original angular velocity angular momentum has to be equal to my final. So this one is I original, omega original is equal to I final times omega final. So we're going to solve again for omega final. That's I original, omega original all over the moment of inertia final. And then this is equal to 1 kilogram meter per meter times second squared. Our original speed was 10, and our final moment of inertia here is going to be 2 kilogram meter second squared. We just added the 2. Since this one was 1 and this one is 1, 1 plus 1 is 2. So now we just take 10 divided by 2, and we get 5 radians per second. So that one's pretty easy. For the next one, this one says a constant force F is applied for a constant time at various points of the object below, shown in the diagram. They want me to go through and rank the magnitude of change in the object's angular momentum due to the force from the smallest to the least. Because the force here is applied right at the fulcrum or right at the pivot point, there is no change in angular momentum, so it would have the smallest change. The next biggest one will be the one that is just near the fulcrum. It's got to be letter C, and it's going right at a 90-degree angle. The next one is either got to be A or D. And if we notice, A is at a slight angle, so we're not getting full force pushing on it, and this one has got a full force. So A has got to be our next answer because it will not have the biggest change compared to D, and then D will have the most change. And that is the end of this section on rotational inertia and conservation of angular momentum.